Hello there and welcome to the Sleepy at Night channel. Tonight, we drift into the quiet wonder of the Milky Way galaxy, the vast river of starlight. We call home a place shaped by ancient suns, powerful forces, and hidden structures far greater than anything the mind can easily imagine. Our galaxy is more than a gathering of stars. It is a living system, molded by billions of years of cosmic history and filled with mysteries waiting quietly to unfold. Picture yourself moving slowly through that enormous expanse where soft clouds of dust glow and faint starlight and hidden currents of energy weave between ancient objects. While colossal clusters float like distant islands in the endless dark, the Milky Way holds wonders formed across unimaginable stretches of time, each one inviting a gentle sense of curiosity. If you enjoy these slow journeys, I invite you to like, subscribe, or share a quiet thought below, helping others find their way. Hear one sleepy soul at a time, but for now, you only need to relax, let the weight of the day fade. Allow your mind to unwind, and let yourself settle as we begin this calm passage through the cosmos. Our galaxy is so vast that light needs 100,000 years to cross it. When you imagine light, you may think of something endlessly swift slipping across a room in an instant, touching your eyes before you even notice it has moved yet. When that same light tries to cross the Milky Way, it becomes almost slow in comparison, taking 100,000 years to travel from one end to the other. The distance is so immense, it stretches the imagination. The space between stars is not entirely empty, but open enough that light wanders freely, brushing past drifting atoms and tiny grains of dust. The scale is so immense that when we look deep into the Milky Way, we are not seeing it as it exists now, but as layers of history spread across unthinkable distances. Light from distant regions began its journey long before any human existed. Every faint shimmer is a fragment of ancient time, reminding us that even the fastest thing in the universe becomes patient when measured against the size of our cosmic home. A supermassive black hole rests at the center of our galaxy with a grip strong enough to bend space. Deep in the heart of the Milky Way lies something that cannot be seen directly yet. Its presence shapes everything around it, a massive black hole hidden behind thick clouds of dust and stars that swirl around it at astonishing speeds. Its gravity distorts the structure of space itself. Stars near the core follow looping paths that expose the invisible mass, guiding their motion far away. Its pull is gentle, but close to the center, it becomes overwhelming. Gas clouds stretch, twist and heat as they fall inward, glowing as they spiral toward the dark heart. Although the black hole itself makes no sound, the region around it pulses with activity created by matter. Rushing into its grasp, this unseen giant anchors the galaxy, shaping its rotation and binding its stars. Imagining something so powerful yet silent invites a deep sense of wonder. The core of our galaxy is no peaceful realm, but a restless domain, ruled by a hidden titan. The Milky Way once swallowed a galaxy nearly half its size. Long ago, a large companion galaxy drifted too near and was slowly torn apart by tidal forces. Its stars, clusters, and sweeping streams of debris absorbed into the halo, forming part of what we see today. Traces of this ancient merger appear as unusually energetic stars and broad arcs of stellar material, marking the remains of the devoured system. Astronomers can still recognize these fragments by studying their motion and chemical signatures, which differ from those of stars born within the Milky Way. This event may have thickened the disk, stirred the dark matter halo, and influenced the formation of the spiral arms. It is a reminder that galaxies grow through acts of cosmic consumption, absorbing entire systems. Across immense eras, the Milky Way carries within it the remnants of this lost giant, a ghostly companion whose stars now shine as part of our own celestial home. Our galaxy is surrounded by dozens of ancient satellite galaxies. Encircling the Milky Way is a quiet community of much smaller galaxies, each holding memories of an earlier universe. These companions drift in wide, graceful orbits, some so faint they nearly disappear into the surrounding dark. Their stars are old, sparse, and delicate, giving them a fragile appearance, yet they influence the evolution of the Milky Way. Their slow movements tug at the outer halos, stirring gentle ripples through the dark matter shroud. Some already shed thin streams of stars, leaving pale trails that wrap around the galaxy like ancient threads. Studying these companions reveals how great galaxies grow, not through sudden violent events, but through countless soft interactions. Spread across unimaginable spans of time, they move like elders circling, a great family, each one holding a chapter of cosmic history that deepens our understanding of how the Milky Way became the spiral we know today. The sun rushes through the galaxy faster than a bullet, though we often imagine it as steady and unmoving. A familiar anchor in the sky, in truth, it is racing through space at a speed far beyond anything we experience on Earth. Carrying every planet, moon, and drifting grain of dust along with it, the sun follows a curved path around the galactic center, shaped by gravity and the combined mass of countless stars. Even though we cannot feel this motion, it is always there, guiding the long future of our solar system and carrying us through shifting regions of the galaxy. As it travels, it passes through gas clouds, gentle radiation fields, and subtle gravitational currents that quietly influence the space around us. This silent journey has lasted billions of years and will continue for billions more, realizing that our familiar star is actually a traveler in a vast orbit invites a quiet feeling of awe. We are passengers on a voyage that never stops. Stars are born in clouds, so cold that fire could never form there. Most people imagine heat and bright flames when thinking about star birth. But the truth is, far more mysterious stars begin in clouds colder than anything on Earth. So cold that fire is impossible, these clouds are made of dust and gas, drifting through the Milky Way, appearing dark because they block the starlight within. Them temperatures fall so low that molecules barely move. Gravity steps in doing what heat cannot. It gathers the cold material and pulls it into dense pockets. As these pockets grow heavier, they contract further. Slowly, pressure warms the center. Over ages, the temperature rises, and only when it becomes unimaginably high does nuclear fusion finally ignite. That moment turns a silent, frozen cloud into a shining star. The idea that brilliant suns begin as cold, shadowy knots of dust feels like a hidden cosmic truth, showing that creation often begins in stillness. Before light appears, the galaxy forms its stars in quiet places. Where warmth is only a distant dream, our solar system floats inside a giant bubble carved by ancient stellar explosions. We live within a vast, hollow region of space without ever sensing it. Long before humans existed, massive stars near our part of the galaxy lived quick lives and died in explosive supernovas. Those explosions cleared away enormous amounts of gas, forming a wide cavity around us. This bubble is filled with thin, hot gas created by the shock waves of those ancient blasts. The material here is far less dense than gas elsewhere in the galaxy, and our sun and planets drift through it as if moving across a quiet room shaped by long-vanished violence. The edge of the bubble forms cooler walls where the leftover shocks slowed down. Astronomers map this structure by tracing faint light emitted inside it, understanding that our entire solar system lies within the remains of ancient stellar giants brings a soft, humbling perspective. We are surrounded by the quiet echo of events that shaped the space we now call home. The Milky Way continues to consume smaller galaxies. Galaxies may appear peaceful, but they are dynamic structures that interact over immense periods of time. The Milky Way is slowly pulling in several nearby dwarf galaxies, stretching their stars into long ribbons that wrap around our own galaxy. These star streams reveal the paths of the smaller systems as they are torn apart. Gravity draws them in until their stars blend with the Milky Way's own population. This process has happened many times and will continue far into the future, explaining the presence of old clusters and unusual stars scattered throughout the galaxy, even now faint companions like the Sagittarius dwarf are being pulled apart as they fall inward. The idea that our galaxy evolves through gentle, relentless cannibalism feels strange yet mesmerizing, reminding us that even structures this vast are shaped by the quiet persistence of gravity. Some stars here are more than twice as old as Earth. The Milky Way contains stars that formed long before our planet existed. Some older than Earth by billions of years. These ancient suns preserve a record of the early galaxy, carrying chemical signatures from a time the universe was young, shedding light on what existed after the first generations of stars lived. and dyed old stars contain fewer heavy elements because those elements had not yet been formed in large amounts by earlier supernovas. Their light is different, their atmosphere is simpler, and their stories far longer. Many of these ancient stars drift through the galactic halo, a sparse region surrounding the Milky Way, moving on wide orbits that lift them high above the spiral arms. Observing them allows astronomers to study the early universe in a quiet, direct way. These old suns burn steadily, holding secrets from a time when the galaxy was still young. Their existence offers a deep sense of continuity, reminding us that long before Earth formed, the Milky Way was already glowing with the light of its earliest stars. The galaxy shines with light from stars too faint for any telescope to see. When we look at the Milky Way on a clear night, the glowing band across the sky is made not only of bright stars but also of countless faint ones, too dim to be seen individually. These stars are small and subtle, yet extremely numerous. Their combined glow forms a soft background light filling the galactic disk. Dust and gas scatter this light, giving the Milky Way its gentle, hazy appearance. Although each faint star is invisible on its own, together they contribute greatly to the mass and structure of the galaxy, shaping its gravity and guiding the motion of brighter stars. Some are old red dwarfs burning quietly, while others are young stars just beginning their long lives. An idea that the galaxy glows with the collective breath of multitudes of unseen suns creates a calm sense of mystery. The light we witness is a whisper from countless small worlds across the sky. Not all planets belong to a star. Some drift freely as rogue planets wandering silently through the darkness. These lonely worlds were likely born in solar systems, but were cast out by gravitational interactions with no sun to warm them. They float through the galaxy in deep cold, their surfaces frozen, yet some may hide warm interiors powered by internal heat. The thought of planets traveling alone offers a haunting beauty. These worlds do not follow neat, predictable orbits, but move on long paths shaped only by the galaxy's gravity. They may pass near stars, drift through clusters, or slip into the outer halo. Although difficult to detect, their existence is supported by simulations and faint observations. There may be far more of them than planets that orbit stars. Imagining these silent travelers gliding through the vast dark between the stars invites a deep, quiet wonder. A giant halo of gas, hotter than any earthly flame, surrounds our galaxy. Far beyond the spiral arms lies a massive envelope of extremely hot gas, stretching high above and below the galactic disk. Its temperature is so intense that it emits faint X-ray light. Though incredibly thin, this gas holds enough mass to influence the movement of stars and small satellite galaxies. This halo is believed to be a relic from the early formation of the Milky Way, along with the ongoing effects of supernovas that push material outward. Also serves as a reservoir of matter that may someday fall back into the galaxy, fueling new stars, though unseen by normal sight. This hot atmosphere envelops everything we know, reminding us that the Milky Way is not just a flat disk, but a layered, intricate structure extending far into space, forming a vast, ancient cloud around us. Radio waves drifting through the Milky Way reveal echoes of long-dead stars across the galaxy. Ancient explosions leave behind signals that travel farther than the fading light of their shattered shells. These signals appear as soft radio waves, gentle but far-reaching. When a star dies in a supernova, its blast sends shocks through space, energizing nearby gas and causing it to glow in radio frequencies. These waves can travel immense distances long after visible light has dimmed. Astronomers use delicate instruments to trace these faint echoes, mapping old remnants hidden behind dusty regions. Each ripple carries clues about the strength of the explosion, the shape of the expanding cloud, and the materials released into space. These signals reveal the secret history of stellar deaths that enrich the galaxy with heavy elements, letting us peer into eras when the Milky Way looked completely different. In this quiet radio glow, the galaxy speaks of its distant past, whispering memories of stars that shone brightly and ended in dignified silence. A teaspoon of a neutron star would weigh more than a mountain. Neutron stars are among the densest objects in existence, formed When massive stars collapse inward after a supernovae, their matter becomes so tightly packed that ordinary atoms cannot survive. Protons and electrons merge into neutrons, creating a substance nothing on Earth can resemble. If you could hold a teaspoon of this material, something no human could truly do, it would outweigh a mountain this unimaginable. Density changes the way light, magnetism, and gravity behave around it. Neutron stars can spin with incredible speed, sending sweeping beams of radiation across space, and they possess magnetic fields far stronger than anything humans can create there. Surfaces are extremely smooth, shaped by gravity, so intense that even a tiny bump cannot last. These strange remnants cool slowly over millions of years, releasing their trapped heat bit by bit. Studying them helps scientists explore the limits of matter and the conditions that exist in extreme environments. The idea that so much mass can be packed into such a small space inspires a deep sense of wonder, reminding us that the universe holds states of matter beyond everyday experience. Milky Way contains star streams that stretch across the sky like ancient rivers throughout the galaxy. Long chains of stars drift together in gentle arcs. These streams are the remains of smaller galaxies and clusters, once whole but gradually pulled apart by the Milky Way's gravity as they stretched their stars scattered along their original paths, forming trails that span enormous distances. Though faint, these streams act as records of past interactions by examining their shapes and motions. Astronomers can trace the histories of the galaxies that contributed them. Some streams rise high above the galactic disk, while others flow quietly within it. They reveal how gravity sculpts the structure of the Milky Way over time, redistributing stars on grand scales. These delicate ribbons also help scientists map the invisible dark matter halo the paths of the stars trace. The unseen gravitational field offering insight into how hidden mass shapes their motion in a quiet way. Star streams show that the Milky Way is always evolving, carrying memories of ancient encounters. Across the sky, new stars ignite in our galaxy. Every second across the Milky Way, star formation never truly rests in cold, shadowed clouds scattered through the spiral arms. New stars arise as gravity pulls gas together into dense pockets. These pockets slowly compress until temperatures climb high, enough for nuclear fusion to begin, marking the birth of a star. This happens so frequently across the vast disk that new stars form every second. Some are tiny red dwarfs, destined to burn softly for trillions of years, while others are larger, brighter, and destined for short, explosive lives. Where star formation occurs is shaped by turbulence, magnetic fields, and the leftover material from older generations of stars. Light from newborn stars gradually clears surrounding dust, revealing bright clusters. Against the dark background, these young stars send out energetic winds, sculpting the very clouds that created them. Constant star birth keeps the Milky Way alive, ensuring that even as older stars fade, new sources of light keep appearing. Some stars spin so rapidly they would fly apart without gravity in the Milky Way. Certain stars rotate at astonishing speeds, their equators racing ahead at hundreds of kilometers per second, far faster than our sun. If not for immense gravity, these stars would tear themselves apart. Their rapid rotation makes them bulge outward, forming flattened shapes. Instead of perfect spheres, this distortion changes their surface temperatures, making their poles hotter than their equators. Fast spin can also produce strong magnetic fields and influence how gas flows around them. Some eject material into space, creating glowing disks or rings. Their extreme speed affects how they live, burn their fuel, and eventually die. Observing them helps astronomers understand how fast a star can rotate before breaking. These rapid rotators reveal a more intense side of the Milky Way, where gravity and motion balance each other with delicate precision, showing that even stars experience tension between stability and the outward forces that push them. Vast cavities in the Milky Way hold enormous regions of empty space. Not all areas of the galaxy are rich with stars and gas. Some are surprisingly open, shaped by ancient events that cleared material away. These giant cavities can span hundreds of light years, forming pockets of thin space within the spiral arms. Many were created by clusters of massive stars whose strong winds and powerful supernovas pushed outward, carving large sections of the surrounding Medium over millions of years, these blasts hollowed out bubbles that drifted, merged, and shaped vast voids within the galaxy. Although these regions contain fewer particles than their surroundings, they are still influenced by the gentle pressure of nearby gas and the gravitational pull of the galaxy. Studying these cavities helps astronomers understand how energy from dying stars shapes the Milky Way. They reveal where clusters once lived and how their activity influenced the surrounding environment. These vast pockets of emptiness contrast with the dense molecular clouds that form stars. They remind us that the galaxy is not uniform but shaped by cycles of creation and destruction that leave behind both bright birthplaces and quiet gaps in the starlit landscape. Diamond worlds exist deep in our galaxy, among the many strange planets in the Milky Way. Some worlds are thought to be rich in carbon to such an extent that their interiors may form diamond-like layers. These planets likely developed in regions where the materials available during their formation were different from those near our Sun. Instead of being dominated by silicate and metals, they contain high amounts of carbon that becomes compressed under intense pressure in the deep interiors of these worlds. That pressure can turn carbon into solid crystalline structures. Similar to diamond, their surfaces might be dark and rocky, but below lies a landscape shaped by exotic chemistry. These planets can orbit close to their stars or drift farther away depending on how they formed. Studying them helps scientists understand the wide variety of conditions that exist across the galaxy. They show that planets can differ dramatically from those in our own solar system. Imagining entire worlds built from carbon-rich materials with glittering layers hidden beneath their crusts offers a quiet sense of wonder. These diamond worlds reveal that the Milky Way holds forms of planetary beauty far beyond anything we have seen on Earth. The Milky Way contains stars that release energy bursts powerful enough to scour planets. Some stars in our galaxy are capable of unleashing sudden bursts of energy that can dwarf the output of normal stellar activity. These bursts can occur when magnetic fields on the star's surface become twisted and then snap, releasing enormous amounts of radiation. The energy can be so strong that it would strip atmospheres from nearby planets or drastically alter their surfaces. These events are rare, but they show how unstable certain stars can be. The bursts travel through space as intense flashes of light and high-energy particles. Even from far distances, they can be detected by sensitive instruments. Studying these outbursts helps astronomers understand the magnetic behavior of stars and the environments around them. Many of these stars are young and still settling into stable patterns of rotation and energy output. Others are older but possess unusually strong magnetic fields. These sudden eruptions remind us that stars are not perfect spheres of calm light. They can be dynamic and unpredictable, sending out powerful pulses that reshape the space around them. Some planetary systems boast dozens of worlds, while our solar system contains a modest number of planets. The Milky Way holds systems far more crowded. Some stars are orbited by dozens of planets, each following its own path through space. These systems form when large disks of gas and dust collapse around young stars. The material gathers into many clumps that grow into planets over time. Because the disks are large and dense, they can produce far more worlds than the one that gave rise to Earth. These planets can be small or large, icy or rocky close to their star, or drifting farther out. Their interactions create complex gravitational patterns that can shift over long periods. Studying these rich systems helps astronomers understand how planets form under different conditions. They show how varied planetary architecture can be, even within a single system. The idea that some stars host entire families of planets far larger than our own adds to the sense of abundance in the Milky Way. It suggests that the galaxy may hold endless varieties of worlds waiting to be discovered. Stars in the Milky Way can be kicked out of their homes and sent wandering alone. Not all stars remain where they were born. Some experience gravitational interactions so strong that they are flung out of their original systems. This can happen in crowded clusters where stars pass close to one another, or when a star's companion explodes in a supernova, abruptly altering the balance of forces once kicked away. These stars travel through the galaxy on long and solitary paths. They move faster than most stars, slipping through the spiral arms and drifting into quieter regions. Although they may appear ordinary in light, Their motions reveal their unusual histories. Studying these runaway stars helps astronomers understand the dynamics of stellar systems and the forces that can disrupt them. These lone travelers offer a glimpse into the more chaotic moments of the galaxy past. They show that even stars can be uprooted by powerful events sent off on journeys that will take them far from their places of origin. Clusters in our galaxy hold stars packed so densely they blur together. In certain regions of the Milky Way, stars gather so tightly that the boundaries between them seem to vanish. These clusters form when large clouds of gas collapse into hundreds or even thousands of stars at once. Because they are born together, they remain close for long periods, before slowly drifting apart inside these young clusters. Stars can be separated by distances far smaller than the gaps between stars near our sun. Their combined light blends into a brilliant glow that fills the sky from within. Some of these clusters are spherical with stars packed densely toward the center. Others form loose associations that still shine brightly through the dust of the galaxy. Studying these clusters reveals details about stellar evolution because the stars within them share similar ages but different masses. Observations show how stars change as they grow, age, and eventually fade. Clusters also play an important role in shaping their surroundings. Their powerful radiation and stellar winds carve out cavities in the surrounding gas, influencing where future stars will form. These crowded stellar communities remind us that many stars are born not in solitude, but in bright, bustling neighborhoods that glow with shared light. Molecular clouds here are massive enough to build thousands of suns. Across the Milky Way lie enormous molecular clouds, vast structures made mostly of hydrogen molecules mixed with dust. These clouds are some of the coldest and darkest places in the galaxy, yet they hold extraordinary potential. A single cloud can contain enough raw material to form thousands of stars the size of the sun. They're immense. Mass allows gravity to shape them into dense knots where new stars take form. These knots collapse over time, igniting nuclear fusion deep within their cores. Despite their scale, molecular clouds are fragile in certain ways. Radiation from nearby massive stars can erode their surfaces, while shock waves from supernovas can compress them, triggering new rounds of star formation. Many of these clouds stretch for hundreds of light years, winding through the spiral arms like shadowed highways of future starlight. They are essential to the ongoing life cycle of the galaxy, holding the ingredients for new solar systems. Observing them requires special instruments because they are opaque to visible light. Inside these dark cradles, entire clusters of stars wait to be born, hidden from view until their light grows strong enough to pierce the surrounding gas. Some stars pulse in brightness like celestial heartbeats. There are stars in the Milky Way whose light rises and falls in rhythmic cycles. These pulsating stars expand and contract as their internal layers shift under the influence of heat and pressure. Each change in size alters the amount of light they emit, creating a pattern that can last hours, days, or months. The pulses act like heartbeats, revealing details about the star's interiors that cannot be seen directly by studying the timing and strength of these pulses. Astronomers can determine a star's mass, age, and temperature. Some of the most well-known pulsating stars are used as cosmic distance markers because their brightness patterns follow predictable rules. These stars help map the structure of the Milky Way by providing reliable measurements for distant regions. Pulsation can occur in young stars, aging giants, or stars in transitional stages of life. Each category has its own signature rhythm. The gentle flickering of these stars adds a quiet sense of movement to the galaxy, reminding us that even stable-looking points of light can contain complex rhythms deep within their glowing layers. Shock waves from ancient supernovas still travel through the galaxy long after a supernova fades from view. The shock wave it created continues to move outward. These waves sweep through the Milky Way like expanding ripples, carrying the energy of the original explosion far across space. As they travel, they compress gas, clouds, heat, interstellar material, and leave subtle changes. In their wake, some shock waves move through regions filled with dust, sculpting it into new shapes. Others pass through emptier areas, gradually weakening, yet still preserving the memory of their violent origins. These shock waves can take tens of thousands of years to expand to their full size. Along the way, they can trigger new star formation by compressing cold regions of gas. They also enrich the interstellar medium with heavy elements created in the supernova modern telescopes can detect. These shock waves, by observing the faint X-ray and radio emissions they appear as expanding shells or filaments that reveal the structure of the surrounding space, even though the star that created them may be long gone. Its influence continues to travel quietly through the galaxy, shaping the environment for future generations of stars. Dust in the Milky Way was forged in the final breaths of dying stars. The dust that fills the Milky Way has a dramatic origin. Much of it was created in the outer layers of aging stars as they reached the ends of their lives. As these stars expanded into red giants, their outer atmospheres cooled enough for tiny solid particles to form. When the stars shed their outer layers, these particles escaped into space. Other types of dust were created when massive stars exploded in supernovas, releasing freshly formed elements into the interstellar medium. Over time, dust grains drifted throughout the galaxy, becoming essential ingredients in the formation of new stars and planets. They help cool collapsing gas clouds, shield molecules from radiation, and provide surfaces on which chemical reactions can occur. Dust absorbs and scatters starlight, giving the Milky Way its soft glow and shaping the appearance of nebula. Each grain carries the legacy of the star that created it. The thought that the dust in the galaxy, and even the dust that eventually formed Earth, came from the dying breaths of ancient stars adds a gentle sense of connection to the larger cycles of cosmic life. A few stars orbit the galactic center with incredible speeds. Near the center of the Milky Way lies a region where gravity grows exceptionally strong. In this dense environment, a handful of stars orbit at extraordinary speeds, far faster than stars located in the more distant spiral arms. These rapid motions were first detected through careful tracking of each star's position over many years. Their tight, fast orbits provide compelling evidence for the presence of a supermassive black hole at the core of the galaxy. As these stars swing close to the center, they follow curved paths shaped by intense gravitational forces. Their motion allows astronomers to calculate the mass of the unseen object controlling their orbits. These stars also help reveal the structure of the central region, which is filled with complex clouds of gas, magnetic fields, and radiation. Despite the extreme conditions, the stars themselves are stable, shining quietly as they trace their dramatic paths. Observing them requires advanced infrared telescopes that can see through the thick dust surrounding the core. Their speed and precision offer rare insight into one of the most mysterious areas of the Milky Way, a place where space is warped by immense gravitational power. Gravity in some regions of the Milky Way warps the shape of starlight. As starlight travels through the galaxy, it can pass near regions of concentrated mass. These areas might be dense star clusters, dark matter structures, or even collections of gas more massive than they appear when light moves through such regions. Gravity bends its path slightly. This bending creates distortions that can magnify, stretch, or shift the appearance of distant objects. Astronomers call this effect gravitational lensing in the Milky Way. Lensing allows researchers to detect objects otherwise invisible, including planets drifting freely and compact remnants hidden in dark areas. It also helps measure the distribution of mass in the galaxy, revealing how much is normal matter and how much is dark matter. The warping of starlight shows that the universe is not flat or simple. Even the light that reaches our eyes has been shaped by the gravity-filled landscape it traveled through. This quiet bending creates a sense of depth and complexity, reminding us that every view of the sky carries subtle traces of the invisible structures that fill the Milky Way. Cosmic rays from our galaxy strike Earth every moment throughout the Milky Way. High-energy particles are constantly accelerating through space. These particles, known as cosmic rays, come from supernovas, energetic stars, and turbulent magnetic fields. They travel at nearly the speed of light and move across vast distances. Even though Earth is protected by its atmosphere and magnetic field, a steady stream of cosmic rays reaches the planet at all times. Most are harmless, interacting with molecules in the upper atmosphere and creating showers of secondary particles that never reach the ground. Studying cosmic rays allows scientists to understand the energetic processes occurring throughout the galaxy. Their energies reveal clues about the violent events that created them. They also help map magnetic fields, since the paths of cosmic rays bend as they move through space. Although invisible, their presence is constant, forming a quiet background of activity around our planet. Cosmic rays show that Earth is not isolated but connected to the energetic workings of the galaxy. They offer a subtle reminder that the Milky Way is a dynamic environment filled with particles and forces that reach even our small world. Some stars are so hot they strip atmospheres from nearby planets. Certain stars in the Milky Way radiate such intense heat and ultraviolet light that they can gradually remove the atmospheres of planets orbiting too close. These stars are often young or unusually massive, burning brightly and releasing powerful winds of charged particles when a planet is exposed to this constant flow of energy. Its upper atmosphere begins to heat and escape into space. Over long periods, the planet can lose much of its air, leaving behind a barren surface. This process shapes the evolution of planetary systems. Some planets may begin with thick atmospheres, but gradually become dry and airless. Observing these interactions helps astronomers understand how stars influence the habitability of surrounding worlds. It also reveals how planetary atmospheres change over time in different environments. Even though the process is slow, the idea that a star's intense heat can reshape an entire world adds a sense of power to the forces at work in the galaxy. These hot stars remind us that every planet depends on the balance between radiation, gravity, and the strength of its own atmosphere. The Milky Way contains magnetic monsters called magnetars. Among the rarest and most extreme objects in the galaxy are these special neutron stars with magnetic fields far stronger than anything found elsewhere. These fields are so intense they can distort atomic structures and influence the surrounding space in unusual ways. Magnetars occasionally release bursts of energy that can briefly outshine all other stars in their vicinity. These bursts come from sudden shifts in the magnetic field, which cause the star's crust to crack. The resulting flare sends powerful radiation into space. Although magnetars are only a few kilometers across, their influence can be felt over great distances. They rotate slowly compared to other neutron stars, but their magnetic power makes them unique. Studying magnetars helps astronomers understand how matter behaves under extreme pressure. The existence of such objects adds a deep sense of mystery to the Milky Way, showing that even among neutron stars, there exist rare and extraordinary members. Magnetars stand as reminders that the galaxy holds phenomena far beyond ordinary experience, where gravity, magnetism, and energy interact in dramatic and surprising ways. Some planets in our galaxy orbit two suns at the same time. Across the Milky Way, there are worlds that do not circle a single star, but move gracefully between these planets. Follow paths shaped by the combined pull of both suns. Depending on the distance and motion of the paraplanet, may orbit the stars together as if they were one glowing center, or weave a more complex path that dips between them. Sunrises and sunsets on such worlds would be unlike anything on Earth. Sometimes both suns rise at once. Other times one sets while the other climbs the sky. The climate on these planets shifts as light and heat change in patterns far different from those on single-star worlds. These systems show how flexible planetary formation can be. Instead of being disrupted by two stars, the disks of gas around them can still gather into stable worlds. Studying them reveals how planets adapt to unusual environments and how common such systems might be. The idea that entire planets orbit twin suns adds a quiet sense of wonder to the Milky Way, reminding us that nature builds with creativity. Antimatter clouds hide near the galactic center. Deep near the middle of the Milky Way lie faint traces of antimatter, a rare form of matter that behaves like an opposite twin to normal particles. These clouds are not bright, but they reveal themselves through the radiation released when antimatter meets matter and annihilates. The origins of this antimatter remain uncertain. It may arise from activity near the central black hole, from energetic interactions among dense clouds, or from the lives and deaths of massive stars. Because antimatter is difficult to create and nearly impossible to preserve its presence in the galaxy, is a quiet surprise. Studying it helps scientists explore high-energy processes that cannot be recreated on Earth. The central region of the Milky Way is a place where intense gravity, magnetic fields, and violent events shape the environment. These faint traces of antimatter show that the heart of the galaxy is alive, with strange and powerful activity. Long tidal streams reveal the ghosts of galaxies we once consumed, stretching across the Milky Way, our delicate flowing trails of stars. Drifting like pale ribbons through the night, these streams are the remains of smaller galaxies torn apart by our own over millions of years. The Milky Way's gravity pulled these companions apart, scattering their stars along their former orbits. Each stream carries the memory of a galaxy that once had shape and structure by studying their motions and their chemical fingerprints. Astronomers can trace the stories of these long-lost neighbors. Some streams rise high above the galactic disk, while others wind through the spiral arms. Their shapes reveal how the Milky Way grows by absorbing smaller systems. They also help map the distribution of dark matter, since their paths bend in response to hidden mass tidal streams, remind us that the galaxy has a long and active past, leaving behind soft echoes of ancient encounters. Binary stars sometimes spiral together until they collide across the Milky Way. Many stars are born in pairs, circling each other in a long dance that can last billions of years. Over time, some pairs drift closer, their orbits shrinking as they exchange energy through tidal forces, through stellar winds, or by interacting with gas around them. Eventually, these stars can fall inward and merge, creating an enormous burst of light and energy, sometimes producing a luminous red nova. The merged star often becomes larger and brighter than either star before the collision. These dramatic unions help enrich the galaxy with heavy elements as material is heated and mixed. Studying them reveals how stars evolve, how rare objects form, and how even quiet pairs can someday ignite with brilliant transformation. Although the process takes an immense amount of time, the idea that two stars can slowly fall toward one another until they become one adds a poetic sense of motion to the Milky Way. Even in the calm night sky, quiet celestial dances are unfolding in ways we can only begin to imagine. Some worlds experience metal or glass rain. Among the thousands of worlds in the Milky Way, some experience forms of weather entirely unlike anything on Earth. On certain hot exoplanets, temperatures soar so high that metals evaporate into vapor, and when the atmosphere cools slightly, these vapors condense into droplets that fall as shimmering metallic rain. On other worlds, strong winds move molten droplets of silicate across the sky, creating storms of molten glass that whip sideways at tremendous speeds. The surfaces of such planets can be glowing oceans of lava, constantly reshaped by violent heat. These extreme conditions occur on worlds that orbit close to their stars or have unusual compositions. Their atmospheres reflect the intense radiation they receive, shaping weather patterns driven by forces unknown on Earth. Observing these exotic climates helps astronomers understand the diversity of environments planets can host, revealing that weather in the galaxy is not limited to clouds or storms of water, but can involve conditions that feel almost otherworldly. These metal and glass rains turn distant planets into shimmering, dangerous landscapes sculpted by heat and alien winds. Repeated supernovas have carved enormous cavities in the Milky Way throughout the galaxy. Massive stars reach the ends of their lives in powerful explosions that send shockwaves into surrounding space, and when many such explosions occur in the same region over millions of years, their combined energy hollows vast cavities. These spaces contain far less gas and dust than their surroundings, appearing as immense bubbles in the interstellar medium shaped by overlapping shock fronts inside them. The gas is hot and thin, while the edges form dense walls where matter has been pushed aside. These structures reveal the history of star formation. Massive stars tend to form together, live short lives, and explode within a brief span, their collective power reshaping the region and influencing where new stars will emerge. Studying these cavities shows how energy flows through the galaxy, marking cycles of birth and destruction that leave behind hollowed regions. Stars exist in intergalactic space after being thrown out of the galaxy. Not all stars remain where they were born. Some are violently ejected during intense gravitational encounters. When a star passes close to a black hole or a dense cluster, it can gain enough speed to escape its galaxy entirely. Once cast out, it becomes a solitary traveler, drifting through intergalactic darkness. Shining like any other star but nearly impossible to detect, Due to its isolation, the Milky Way has thrown out many such stars over its long existence, some expelled during galaxy collisions, others flung away when their companions exploded, changing the balance of forces. Studying these runaway stars reveals the extreme events that unfold across galaxies, reminding us that the universe is full of motion and change, where even stars can be cast adrift. These wanderers glide through the dark, carrying the story of the violent moments that freed them. The Milky Way holds ancient star clusters older than any planet scattered throughout the galaxy. Are globular clusters, dense spheres of stars formed when the Milky Way was young. Many are older than Earth, older than the Sun, and older than every known planet. They contain some of the earliest generations of stars. Created before the galaxy settled into its spiral form, the stars within move in tight orbits packed closely enough that the sky would glow brilliantly if seen from inside. Their chemistry reveals what the young universe was like before heavy elements were common. These clusters orbit far from the galactic disk, drifting through the halo on long looping paths. Observing them helps scientists trace the history of the galaxy and understand how its first structures formed. Their immense age gives them a quiet dignity. They have survived collisions, mergers, and countless cosmic events, remaining ancient survivors in a galaxy transformed since they first lit the darkness. Some stars in our galaxy rotate with blinding beams. Like cosmic lighthouses, there are pulsars rapidly spinning, neutron stars that emit intense beams of radiation from their magnetic poles. As they rotate, these beams sweep across space, and when the beam aligns with Earth, we see a pulse repeating with perfect regularity. Like a cosmic lighthouse turning through the night, formed when massive stars collapse after supernovas, pulsars stand as powerful reminders of the forces shaping the universe. Their rapid rotation and intense magnetic fields make them unique among stellar remnants. Some pulsars spin several times per second, while others whirl hundreds of times within the same moment. Their steady pulses help astronomers measure distances, map regions of the galaxy, and explore the boundaries of fundamental physics. Pulsars reveal how matter behaves when compressed to unimaginable densities. They also deepen our understanding of gravitational waves, as pairs of pulsars orbiting each other can create ripples in space-time. These cosmic lighthouses add rhythm to the Milky Way, sending precise signals through the darkness that let us study remote regions with remarkable clarity. Certain regions glow with radiation from past cataclysms. Throughout the galaxy, faint yet persistent radiation marks the lingering energy left behind by ancient events such as supernovas, gamma-ray bursts, or collisions between dense clouds of gas and high-energy particles. These areas may no longer contain the sources that created the disturbance, yet the glow remains as a signature of their violent history. It often appears in wavelengths invisible to the human eye, like X-rays or gamma rays. Observing these places reveals hidden chapters of the Milky Way, showing where powerful forces once sculpted the environment. Some of the radiation comes from electrons spiraling through magnetic fields, or from superheated gas. These glowing regions stand as reminders that the galaxy has endured many energetic episodes. Even though the original explosions occurred long before humanity existed, their echoes still drift through space. This quiet radiation tells stories of ancient power still etched into the fabric of the galaxy. At the galactic center, clouds move with speeds that defy intuition. Near the heart of the Milky Way, gas clouds behave in ways that seem unreal, orbiting close to the central black hole, where gravity becomes extreme. Some clouds race around the core at hundreds of kilometers each second, following stretched looping paths shaped by the uneven distribution of mass. The region is filled with radiation, magnetic fields, and swarms of fast-moving stars, creating turbulence that twists and distorts the clouds into strange forms. Thick layers of dust block visible light, so astronomers use infrared and radio telescopes to observe them. Tracking their movements reveals gas rushing, colliding, and spiraling through patterns that expose the hidden structure of the core. These rapid motions also help scientists estimate the mass of the central black hole by showing how strongly it pulls on everything nearby. The pace and energy of this region sharply contrasts with the calm night sky deep inside the galaxy. Clouds race and churn at unimaginable speeds, driven by forces far stronger than anything near Earth. Some worlds orbit their stars in minutes instead of years. Not all planets follow the slow, sweeping orbits familiar from our solar system and the Milky Way. Some worlds circle their stars so closely they complete an entire orbit in minutes. These ultra-short period planets cling tightly to their stars, the star-facing side scorched by heat, while the far side remains much cooler. Intense gravity and fierce radiation strip these planets of their outer layers, often leaving behind dense, rocky cores. Their closeness to their stars means they move at astonishing speeds, sometimes racing tens of kilometers each second. Studying these worlds reveals how planets evolve under extreme conditions, showing how orbits shrink and how worlds adapt to fierce heat. These rapid orbits create unusual cycles of day and night, a year lasting only minutes. Challenges our sense of planetary motion and highlights the astonishing variety of systems across the galaxy. The Milky Way contains planets made almost entirely of water. Among the countless worlds in our galaxy, some are believed to be dominated by water in forms unlike anything on Earth. These planets may contain vast stores of high-pressure ice and superheated liquid layers. Buried beneath thick atmospheres under extreme pressure, water can take exotic forms, creating dense, crystalline structures. These planets are often larger than Earth, with strong gravity that holds their deep global oceans. Some may hide rocky cores beneath hundreds of kilometers of water. Studying them helps astronomers understand how planets form under different temperatures and materials. Their existence broadens the idea of what a habitable world can be. Instead of continents and seas, these planets might be endless global oceans, with no land at all. Imagining entire planets shaped by water, yet entirely unlike Earth, brings a sense of quiet wonder to the Milky Way. They remind us that planetary diversity is far greater than once believed. Not every star in the galaxy burns with fierce heat. Some are so cool and faint that their temperatures barely exceed those of giant planets. These ultra-cool dwarfs emit most of their light in infrared wavelengths, making them nearly invisible to the unaided eye. Despite their small size, they are true stars, powered by steady nuclear fusion of hydrogen deep within their cores. Their low temperatures allow molecules to form in their atmospheres, creating complex patterns of light absorption. Studying these stars helps astronomers understand the lower limits of stellar formation. They also provide clues about how planets might appear from a distance. Some of these cool stars host planetary systems where temperatures are gentle enough to allow a wide range of conditions. Because they shine so softly, life on planets orbiting them would experience a dim, reddish world. These stars remind us that the Milky Way contains many forms of starlight, from blazing giants to quiet, ember-like suns that blur the line between star and planet. The galaxy contains enormous arcs of gas that stretch for light years. Threaded through the Milky Way are immense arcs of gas spanning incredible distances, shaped by stellar winds, supernova explosions, and magnetic forces pushing and pulling the material over time. Some arcs form curved walls around old cavities. Others trace long paths created by the motion of massive stars drifting through the interstellar medium. Because the gas is often thin and cold, it can be difficult to detect. Invisible light, radio, and infrared telescopes reveal delicate curves stretching across hundreds of trillions of kilometers. These arcs help astronomers understand the history of star formation. Their shapes reveal past explosions, the flow of energy through the galaxy, and the way clouds respond to gravity and pressure. They act like enormous cosmic brushstrokes, marking areas where powerful forces once swept through. Seeing these shapes mapped across the Milky Way adds a sense of artistry, as if vast hands shaped its gas into beautiful curved forms. Some star clusters drift together through space for ages. Groups of stars travel in harmony across great distances. These drifting clusters form when stars are born together within a single cloud of gas. Over time, gravitational interactions with other stars and clouds gently pull the cluster apart, yet many stars continue moving in the same general direction. These groups can persist for hundreds of millions of years, maintaining similar speeds and positions even as they spread out. Because the stars share a common origin, they have similar chemical compositions, and ages studying these moving groups helps astronomers trace the history of star formation and understand how clusters dissolve over time, they also reveal how stars migrate through the galaxy, drifting from their birthplaces into new regions. Some moving groups eventually blend into the background population of the Milky Way. Others remain coherent for long stretches, like quiet caravans traveling across the galactic landscape. Their gentle motion adds a sense of continuity, showing how stars carry their shared beginnings as they drift. The Milky Way has stars that blast jets of particles across space. Certain stars produce narrow, powerful jets shooting outward. At tremendous speeds, these jets often form when material spirals onto a dense object such as a neutron star or a young star surrounded by a disk of gas. As the material falls inward, magnetic fields twist and focus it into slender streams leaping into space. The jets can travel for light years, illuminating surrounding gas and carving paths that reveal the structure of the region in young stars. Jets help clear leftover material from formation in older, more compact stars. The jets can become extremely energetic, producing radiation detectable across. There's the galaxy. These dramatic phenomena show how magnetic fields and gravity combine to create powerful, elegant structures. The sight of a star launching focused streams of energy into the dark reminds us how dynamic and creative the universe can be. Even small systems can produce effects reaching far beyond their immediate surroundings. A few stars move so fast they will escape our galaxy forever. Most stars follow stable orbits shaped by the galaxy's mass. However, a rare group travels at extraordinary speeds, fast enough to leave the Milky Way entirely. These hypervelocity stars are launched by powerful gravitational interactions, or slingshot by the central black hole when they pass too close. Others are released when their binary partners explode suddenly, freeing them from orbit once accelerated. These stars move on long paths outward, eventually drifting into intergalactic space. They shine like ordinary stars but carry unusual velocities that reveal their dramatic histories. Studying them helps astronomers understand the extreme conditions near the galactic center and the outcomes of supernova explosions. These runaway stars remind us that even massive galaxies cannot hold all their members forever. Some will break free, carrying their light into the empty space between galaxies. Their journeys will last for billions of years, silent and solitary, shaped by the moment that set them on their way. Some regions in the Milky Way are filled with electricized plasma clouds scattered throughout the galaxy. Are clouds made not of cold gas, but of energized plasma. These regions contain charged particles that respond strongly to magnetic fields. As a result, they behave differently from ordinary gas clouds. They can twist into filaments, ripple like waves, or glow with soft light generated by electrons spiraling through magnetic structures. Many of these plasma clouds are created by massive stars or supernova explosions that pump energy into their surroundings. Others are shaped by turbulence in the interstellar medium. Studying these regions provides insight into the magnetic environment of the Milky Way, which cannot be observed directly. Plasma clouds help astronomers trace the invisible fields that thread the galaxy. They also influence how cosmic rays travel, guiding or deflecting them as they move. These charged regions add another layer of complexity to the Milky Way. They reveal that the spaces between stars are not empty, but filled with subtle energy shaped by both matter and magnetic forces. Giant nebulae glow with colors created by energetic young stars throughout the Milky Way. There are vast nebulae lit by the presence of young, massive stars. These stars emit intense ultraviolet light that energizes the surrounding gas, causing it to shine with vivid colors. Hydrogen glows in soft reds, while oxygen can produce gentle greens or blues. These glowing clouds are often birthplaces of new stars inside them. Dense pockets of gas collapse into young suns that eventually emerge from the surrounding material. The shapes of nebula are sculpted by stellar winds, radiation, and turbulence, forming arches, pillars, and cavities that create some of the most striking scenes in the galaxy. Studying these nebula helps astronomers understand how stars form and how they influence their environment. The glowing clouds also reveal the chemical makeup of the galaxy, since different elements produce different colors when energized. These luminous regions remind us that starbirth is both powerful and beautiful. They fill the Milky Way with soft, colorful light, transforming ordinary gas into radiant sculptures. Shaped by the presence of young and energetic stars, the galaxy holds hidden brown dwarfs that never became full stars. Brown dwarfs fill a quiet space between planets and stars. They form when clouds of gas collapse, just as they would during star formation, but the resulting object never gathers enough mass to ignite full nuclear fusion in its core without this steady source of energy. Brown dwarfs shine, only faintly glowing softly. With leftover heat from their formation, they can have masses far greater than planets, yet remain too cool and dim to appear as stars, because their light is weak and mostly emitted in infrared wavelengths. Many remain unseen, drifting quietly through the Milky Way. These elusive objects help astronomers understand the lower limits of star formation. Their atmospheres contain unusual molecules shaped by cool temperatures and high pressure. Some brown dwarfs exhibit weather patterns that shift over hours or days, revealing dynamic behavior in their cloud layers. Although they do not burn like true stars, they play an important role in the galaxy's population. They fill the spaces between bright stars, adding hidden complexity to the Milky Way. Their gentle glow and mysterious nature offer a reminder, but not all celestial bodies fit neatly into familiar categories. Some worlds are covered in lava oceans. Certain exoplanets orbit so close to their stars that their surfaces melt into glowing seas of molten rock. These lava worlds are shaped by intense heat that prevents solid crust from forming. Instead, their surfaces churn with rivers of liquid stone that slowly flow under the pull of gravity and the motion of atmospheric winds. The temperatures on these planets can exceed the melting points of many minerals, turning their landscapes into luminous red and orange vistas. Some of these worlds also experience tidal forces from their stars, which cause their interiors to heat even more. As a result, volcanic activity can become widespread, feeding lava oceans that constantly renew themselves. Studying these extreme planets helps astronomers understand how worlds evolve under extreme radiation their atmospheres can contain. Vaporized rock that condenses into mineral clouds. When these clouds cool, they can produce unusual forms of precipitation that fall back into the molten surface. Lava worlds show that planetary environments in the galaxy are very far beyond anything seen on Earth. They offer a glimpse into cosmic landscapes forged by heat and motion in the harshest possible conditions. Pulsars in the Milky Way spin with the precision of cosmic clocks. Pulsars are rapidly rotating neutron stars that send beams of radiation out from their magnetic poles. Each time a beam sweeps past Earth, it produces a pulse of light that arrives with remarkable regularity. Some pulsars maintain timing so consistent that they rival atomic clocks in stability. This precision makes them valuable tools for studying the galaxy by observing slight changes in pulse timing. Astronomers can detect the influence of passing objects, gravitational waves, or movement within the pulsar itself. The rotation of a pulsar is a relic of the star that created it. When a massive star collapses, its core shrinks dramatically, causing it to spin faster. In the same way, a spinning ice skater speeds up when drawing in their arms, although pulsars gradually slow over millions of years. Their early stages can feature hundreds of rotations each second. Their intense magnetic fields guide charged particles along narrow paths, creating the beams that make them so distinctive. Pulsars serve as natural laboratories for extreme physics, revealing how matter behaves under conditions far beyond any experiment on Earth. The galactic center hides vast stores of molecular gas. Deep within the central regions of the Milky Way lies an enormous reservoir of molecular gas. This material is dense, cold, and rich in the ingredients needed for star formation. However, the center of the galaxy is not a quiet or simple place. Strong radiation fields, turbulent motions, and intense gravity affect the gas constantly. Clouds are stretched, compressed, and heated as they orbit close to the central black hole. Despite the harsh environment, pockets of gas remain shielded enough for molecules to survive. These regions form some of the most massive and active star forming. Them requires using radio and infrared wavelengths that can penetrate the thick dust surrounding the core. The distribution of this molecular gas helps astronomers understand how stars form under extreme conditions. It also reveals how energy moves through the galactic center, shaping the evolution of nearby regions. These hidden stores of gas play a crucial role in building new generations of stars, showing that even the most intense environments can be fertile grounds for creation there. Are double planet systems that orbit each other like dance partners? Not all planets revolve around stars alone in rare cases. When two planets of similar mass form close enough to one another that they share a mutual orbit instead of one dominating the pair circles a common center of gravity located between them, these double planet systems move through space like partners. Performing a slow and graceful dance, their shared motion affects their rotation, their tides, and their long-term stability. Finding such systems is challenging because they often resemble single planets. When viewed from afar, however detailed, observations can reveal small variations in their orbits that hint at their dual nature. These systems provide insight into how planets form and interact. They show that worlds can develop in cooperative pairs rather than solitary paths. The existence of such arrangements highlights the diversity of planetary configurations possible in the Milky Way. Imagining two planets bound together in a cosmic waltz adds a touch of elegance to the vast and varied structures scattered across the galaxy. Some stars are shaped into flattened spheres by extreme rotation. Certain stars rotate so quickly that they become noticeably flattened. Their equators bulge outward due to centrifugal force, while their poles remain more compact. This shape affects the distribution of temperature across the surface. The poles tend to be hotter and brighter because the material there is more compressed, while the equator can appear cooler. This phenomenon is known as gravity darkening. Rapidly rotating stars are often young and massive, still carrying the angular momentum of their formation. Their rotation also influences how they evolve. Fast-spinning stars can mix their internal layers more efficiently, changing the way they burn fuel. Observing these stars helps astronomers understand the complex interactions between rotation structure and energy output there. Distorted shapes challenge the simple idea of stars as perfect spheres. They reveal that even familiar-looking points of light can hide unusual physical behavior. These flattened stars add another level of diversity to the Milky Way, showing that rotation can sculpt a star into forms very different from the ones we see near home. Massive supernova remnants still glow with fierce energy. When a massive star explodes, it leaves behind a cloud of gas and debris known as a supernova remnant. These remnants expand outward for thousands of years, interacting with the surrounding interstellar medium even long after the explosion has faded from view. The remnants continue to glow. Shockwaves heat the gas to high temperatures, producing X-rays and visible light. The filaments and knots within the remnant reveal details about the original star and the force of the explosion. Studying these remnants helps astronomers understand how heavy elements are dispersed throughout the Milky Way. They also show how energy from dying stars shapes nearby regions over time. The expanding remnant slows and cools, eventually blending into the surrounding gas, yet during its active phase, it stands as a brilliant reminder of the dramatic events that occur when massive stars reach the ends of their lives. These glowing clouds show that the aftermath of a supernova remains vibrant and full of information long after the initial flash has faded. Some planets skim so close to their stars they glow red-hot. In the Milky Way, there are planets that orbit so near their stars that their surfaces heat to extreme temperatures. These close-in worlds are often large and gaseous, with atmospheres that swell and shimmer under the intense radiation. The heat causes their clouds to glow sometimes, giving the entire planet a reddish or golden hue. Their dayside temperatures can vaporize minerals and metals, creating exotic atmospheric chemistry. The intense stellar winds constantly strip away particles from their upper layers, forming long tails of gas that trail behind them. These planets complete orbits quickly, sometimes in only a few days. Studying them reveals how planets adapt to being in such harsh proximity to their stars. Their structure, weather, and atmospheric escape provide valuable clues about planetary survival under extreme conditions. These red-hot worlds show that the Milky Way contains planets far stranger and more varied than the ones found in our solar system. The Milky Way contains clouds where ice crystals form in space, in the coldest regions of the galaxy, far from intense starlight. Clouds of gas can become cold enough for molecules to freeze onto tiny dust grains. These frozen coatings form delicate Ice crystals made of water, carbon dioxide, methane, and other compounds. These crystals play an important role in the chemistry of the interstellar medium. They provide surfaces where complex molecules can form gradually, building the raw materials that may one day contribute to planets or even life. Infrared observations reveal the presence of these ices by their distinctive absorption patterns. These frozen clouds hide their treasures behind thick veils of dust. Studying them helps astronomers understand the earliest stages of star and planet formation. They show how cold and quiet the galaxy can become. In its most sheltered corners, these icy environments act as gentle incubators, where chemistry unfolds slowly over millions of years. Ancient red giants fill the galaxy with heavy elements. Red giants represent a late stage in the life of many stars. As they exhaust the hydrogen in their cores, they expand and cool, becoming large and luminous inside. These vast envelopes, new elements, are forged through nuclear reactions over time. Red giants shed their outer layers, releasing these elements into the interstellar medium. This material becomes part of the gas and dust that will form new stars and planets. In this way, red giants enrich the galaxy with the building blocks for future generations of celestial bodies. Their slow and steady winds carry carbon, nitrogen, and other essential elements far into space. Observing red giants helps scientists understand the chemical evolution of the Milky Way. Their gentle glow and constant contribution to the cosmic cycle add a sense of continuity to the galaxy. They remind us that creation and renewal are woven into the life of every star, even those nearing the end of their luminous journey. Some stars wander on orbits that stretch across half the galaxy. Not all stars follow neat circular paths around the Milky Way. Some move on long-stretched orbits that carry them from one side of the galaxy to the other. These stars travel through regions with very different densities of gas, radiation, and gravitational pull. Their elongated paths often form when the stars originate in satellite galaxies that were later absorbed by the Milky Way. As these smaller galaxies broke apart, their stars were captured and set on wide ranging orbits. Other stars may have been thrown into eccentric paths by close encounters with massive objects. Their journeys take them far above the galactic plane, then back down through the spiral arms. Observing these travelers allows astronomers to study the structure and mass of the galaxy on large scales. Their motions reveal how the Milky Way's gravitational field changes from one region to another. These wandering stars act as quiet messengers from the galaxies past, carrying evidence of long-vanished mergers and ancient interactions. Their wide orbits show that the Milky Way is not a static disk, but a dynamic system shaped by countless events. The galactic halo contains faint stars that drift like cosmic ghosts surrounding. The bright disk of the Milky Way is a vast halo filled with extremely old and faint stars. These stars drift through space with slow and steady motion, far from the bustling regions where new stars are born. Many of them formed in the earliest eras of the galaxy before the spiral arms took shape. Their low brightness makes them difficult to detect, and their wide distribution means they are separated by great distances. These halo stars often have unusual chemical compositions containing very small amounts of heavy elements. Studying them helps astronomers understand the conditions that existed shortly after the universe began forming stars. Some halo stars belong to ancient clusters that have survived for billions of years. Others were once part of smaller galaxies that merged with the Milky Way. Because the halo is so sparse, its stars appear isolated, shining quietly against the deep background of space. These drifting lights remind us of the Milky Way's earliest chapters, still present even after the galaxy has changed dramatically over time. There are worlds locked in perpetual twilight between their stars. In some binary star systems, a planet can settle into an orbit that places it between two stars in a balanced configuration. When this happens, the combined light from the pair can create a world bathed in constant twilight. The sky would never become fully dark and true. Day might never arrive. The lighting on such worlds would shift softly as the stars move in their own orbit, but darkness would remain. Rare temperatures on these planets depend on the distance from the stars and the intensity of their light. Some of these twilight worlds may be mild, while others could be cold or even warm enough to allow liquid water the gravitational forces from two stars create. Complex patterns in the planet's orbit, yet many of these configurations remain stable for long periods. Studying such systems shows how planetary environments can vary in surprising ways. Reveal that sunlight is not always simple or singular. These dusk-lit worlds offer a picture of planetary life shaped by soft and constant glow. Stellar nurseries in the Milky Way can spawn entire star clusters at once. Deep within the Milky Way lie vast regions of cold gas where new stars are born. These stellar nurseries often produce not just single stars, but entire clusters. As gravity pulls large quantities of gas together, the material breaks into many dense pockets. Each pocket can collapse into a star, leading to the formation of groups that emerge together. These clusters often contain stars of many different sizes, from massive blue giants to small red dwarfs. The stars interact through their gravity and radiation shaping the environment around them. Young massive stars create strong winds and intense light that carve out cavities in the surrounding gas. These processes can trigger additional star formation or halt it depending on how the material is affected. Once the gas is cleared, the newly formed cluster begins to drift through the galaxy. Over time, some clusters remain intact, while others slowly dissolve. Studying these nurseries reveals how the Milky Way continues to renew itself, building new generations of stars and waves of creation. Some stars shed their outer layers in vast shimmering shells. As certain stars near the end of their lives, they undergo changes that cause them to shed their outer layers. These layers expand into space, forming large glowing shells of gas surrounding the dying star. The shells appear luminous because the remaining core heats the gas, causing it to emit soft light. These elegant structures are called planetary nebulae, although they have nothing to do with planets. Each one carries unique shapes formed by the stars' rotation, magnetic fields, and the motion of surrounding material. Some nebula form rings, others take on butterfly-like forms, and still others appear spherical. Over time, the gas disperses into the surrounding space, enriching the interstellar medium with elements created inside the star. These shimmering shells represent a brief but beautiful phase in the life cycle of low to medium mass stars. They provide vital clues about how stars evolve and how they contribute new material to the galaxy. Their delicate structures transform the quiet death of a star into a luminous event that ripples outward for thousands of years. The Milky Way contains strange carbon stars that burn with deep crimson light. Among the many stars in the galaxy, some shine with an unusually rich red color. These carbon stars have atmospheres filled with carbon compounds that absorb blue light and allow deep crimson tones to dominate. They form when aging stars dredge up carbon from their interiors and release it into their outer layers. This process changes the chemical balance of the atmosphere and gives the star its distinctive appearance. Carbon stars often appear especially bright in infrared wavelengths, making them stand out in surveys of the galaxy. They also produce dust that enriches the interstellar medium. Studying these stars helps astronomers understand how elements are cycled through stellar evolution. Their red glow adds diversity to the Milky Way's population of stars, showing how different chemical processes can influence the appearance of starlight. These stars burn with a warm and gentle radiance, offering a reminder that even small changes in composition can create dramatic effects in the light. We see some worlds are tidally locked and never see a sunrise. Many planets orbit their stars in such a way that the same side always faces the light. These tidally locked worlds have a permanent day side and a permanent night side. On the day side, temperatures can become extremely high, while the night side may be frozen in perpetual darkness. A narrow region between the two sides, known as the twilight zone, can maintain more moderate conditions. Atmospheres on these planets move heat around, shaping wind patterns and clouds in ways that differ from those on Earth. Some tidally locked worlds orbit small, cool stars where the habitable zone lies close to the star despite their unusual lighting. These planets may still be capable of supporting liquid water under the right conditions. Studying Them helps astronomers understand how climates function when sunlight never shifts tidally locked worlds. Show the range of environments possible. In the galaxy, they remind us that day and night concepts familiar to us can take on entirely different meanings elsewhere. In the Milky Way, giant bubbles of radio emission rise above the galactic center, towering above and below the Milky Way's central region are enormous bubbles that emit faint radio waves. These structures extend for thousands of light years and are filled with energized particles. The bubbles likely formed from past activity near the central black hole or from bursts of star formation that released vast amounts of energy. Their smooth outlines suggest powerful forces sculpted them, pushing gas outward into large lobes. Observing these bubbles helps astronomers understand the energetic history of the galaxies. Core inside them, charged particles spiral through magnetic fields, producing the radio emission that reveals their shape. The scale of these bubbles is difficult to grasp. They rise far above the disk, forming some of the largest structures in the Milky Way. Their presence shows that the galaxy's center has undergone dramatic episodes that shaped vast regions of space. These giant bubbles act as markers of ancient events, whose echoes still linger in the quiet radio glow. They are a black hole. Pairs hidden throughout the galaxy, black holes are often found not alone, but in pairs formed when two massive stars evolve together. As each star reaches the end of its life, it collapses into a black hole. The pair then orbits a common center of gravity, slowly drawing closer as they lose energy through gravitational waves. These hidden systems are difficult to detect because black holes emit no light. Astronomers identify them by observing the motion of nearby stars or by detecting high energy radiation when one black hole pulls material from a companion star. Some pairs remain quiet for long periods, revealing themselves only through subtle gravitational influences. These binary black holes hold valuable clues about stellar evolution. The death of massive stars and the conditions that lead to gravitational wave events, their silent motion, adds an air of mystery to the Milky Way. They drift unseen through the galaxy, locked in orbits that will eventually end in a powerful merger, releasing energy across space. Some stars form with entire disks of dust that glow like embers. Young stars often emerge surrounded by disks of dust and gas. These disks glow with gentle warmth as starlight heats the small particles within them. The dust absorbs energy and re-radiates it in infrared wavelengths, creating a soft ember-like glow. These disks are the birthplaces of planets. Over time, dust grains collide and stick together, forming larger clumps that grow into planetesimals and eventually full planets. The structure of these disks can reveal the earliest stages of planetary formation. Rings, gaps, and spirals may appear as new worlds carve paths through the dust. Observing these glowing disks helps astronomers understand how solar systems emerge from simple clouds of material. They show that planets begin as tiny grains drifting in warm, swirling environments. These softly lit disks offer a glimpse into the beginning of worlds, shining as delicate halos around the stars. They nourish the Milky Way, holds worlds larger than Jupiter, but float alone. Scattered throughout the galaxy are enormous planets that drift freely without orbiting any star. These rogue giants can be larger than Jupiter and wander through space in cold silence. They likely formed in young planetary systems but were later flung out by gravitational interactions with other large bodies. Once ejected, they continue on solitary paths, illuminated only by the faint glow of their internal heat. Some of these planets may still retain thick atmospheres that trap warmth. Others may harbor swirling storms that churn slowly in the deep dark. Detecting these worlds is challenging because they do not reflect starlight. Instead, astronomers search for the faint infrared radiation they emit or watch for subtle gravitational effects when they pass in front of distant stars. These lonely giants reveal how dynamic and chaotic planetary systems can be. Their existence suggests that planets are not always bound to the stars that form them. Instead, they may roam indefinitely through the galaxy, traveling far from any warmth or light. These wandering worlds add a quiet and mysterious dimension to the Milky Way's population of planets. There are stars that feed on their companions. In some binary systems, one star grows dense enough to draw material from its partner, This process can occur when a star becomes a white dwarf neutron star or black hole. The stronger gravitational pull of the compact object strips gas from the companion's outer layers. This material forms a swirling disk around the feeding star, heating up as it spirals inward. The interaction can produce bursts of radiation that appear as bright flares in the sky. Over long periods, the feeding star may gain significant mass, altering its behavior and sometimes setting the stage for future explosive events. Star being consumed may lose much of its outer envelope, changing its structure and evolution. These dramatic relationships reveal how closely paired stars can influence one another. They show that stellar life cycles are not always solitary. Instead, some stars grow by taking material from their neighbors, creating systems shaped by both cooperation and conflict. These feeding stars remind us that even distant suns can experience intense and transformative interactions. Some planets orbit dead stars. Although it may seem unlikely, planets can survive the dramatic transformation of a star into a stellar remnant. Some orbit white dwarfs, the hot cores left over after stars like the Sun shed their outer layers. Others circle neutron stars, which form from the collapse of massive stars. These environments are harsh, flooded with intense radiation. Yet some planets endure. They may have formed after the stars' death, assembling from leftover debris, or they may have migrated inward over time around white dwarfs. A planet can receive stable light and heat once the remnant cools enough around neutron stars. Conditions can be extreme, with strong magnetic fields influencing the planet's atmosphere. The presence of planets around dead stars challenges assumptions about planetary survival. It shows that worlds can persist even after dramatic cosmic events. These planets offer insights into how systems rebuild themselves and how diverse planetary environments can be. They serve as reminders that even the aftermath of stellar death give rise to new and surprising structures. The galaxy contains regions rich with organic molecules. Across the Milky Way are clouds filled with complex organic molecules. These molecules form on the surfaces of dust grains or within cold gas, combining simple elements into intricate structures. Some of these molecules are precursors to the chemistry found in living organisms, although their presence does not imply life. Instead, they show that the building blocks of biology can arise naturally in many environments. These regions are often located in dense molecular clouds where temperatures are low and ultraviolet. Radiation is limited. Infrared and radio telescopes detect the signatures of these molecules, revealing their abundance. Their presence suggests that chemistry in the galaxy is rich and varied. Understanding how these molecules form helps astronomers learn about the early stages of planetary development. They may eventually become part of comets, asteroids, or even planets. The idea that organic complexity exists in quiet clouds scattered throughout the Milky Way brings a sense of connection to the broader universe. It shows that the seeds of chemistry are widespread, waiting for the right conditions to unfold. Ancient supernova debris still drifts through the Milky Way. When massive stars explode, they send debris far into the galaxy. This material includes heavy elements that were forged inside the star before it died. Over time, the debris spreads out, forming filaments and clouds that drift through the interstellar medium. Some of this material mixes with molecular clouds, becoming part of the next generation of stars and planets. Other fragments remain isolated, glowing softly as they cool. Studying these remnants helps astronomers understand the composition of supernovas and how elements move through the galaxy. These drifting clouds can be detected in many wavelengths, from radio waves to X-rays, depending on their temperature and structure. They serve as markers of the powerful events that shaped the chemical landscape of the Milky Way. The debris acts as a bridge between generations of stars, carrying the legacy of long-dead giants into the future. Even after millions of years, these remnants continue to influence the evolution of the galaxy. There are stellar bow shocks created when stars plow through gas, as some stars move rapidly through the galaxy. They encounter clouds of gas that stand in their path. The interaction creates a bow-shaped shockwave similar to the wave formed by bobbies. A boat moving through water, this shock compresses and heats the gas, causing it to glow in infrared or visible light. The shape and brightness of the bow shock depend on the star's speed, wind strength, and the density of the surrounding material. These structures reveal important information about both the star and its environment. They show how stellar winds push against the interstellar medium and how stars respond to the gas around them. Some bow shocks stretch across light years, forming graceful arcs that mark the star's motion. Observing them helps astronomers track runaway stars and understand how high-speed interactions shape the galaxy. These luminous curves offer a reminder that even the motion of stars can paint patterns. In the surrounding gas the Milky Way contains massive hot stars that live fast and die young. Among the stars in the galaxy are a rare group of giants that burn their fuel at an incredible rate. These massive hot stars shine with intense brightness and produce strong, stellar winds that shape their surroundings. Because they consume their hydrogen quickly, they live only a few million years. A brief moment in cosmic terms, their ultraviolet radiation influences nearby clouds, triggering star formation or halting it depending on the conditions. When these stars reach the end of their lives, they explode as powerful supernovas, releasing heavy elements into the interstellar medium. Studying them helps astronomers understand how energy flows through the galaxy. Their short but intense lives play an important role in the evolution of surrounding regions. They sculpt nebula, enrich the galaxy, and leave behind compact remnants such as neutron stars or black holes. These fast-living giants show that not all stars follow gentle paths. Some blaze brilliantly for a brief time, leaving lasting marks on the Milky Way. Some worlds experience constant storms larger than Earth. Across the galaxy, there are planets where storms never truly end. These colossal weather systems can span distances larger than Earth itself and may persist for years or even centuries. Many of these worlds are gas giants with thick atmospheres dominated by strong winds and powerful jet streams. The storms form where bands of atmospheric motion collide, creating swirling vortices that grow into immense cyclones. Some storms appear as bright or dark spots that shift in size and shape over time. Their colors reflect the chemical composition of the clouds and the temperatures within the storm. Studying these massive weather systems helps astronomers understand the dynamics of planetary atmospheres under different conditions. The presence of such storms shows how lively and turbulent distant worlds can be. These powerful systems remind us that weather in the Milky Way is not limited to gentle breezes or moderate rains. Instead, some planets host storms with scales and energies far beyond anything experienced on Earth. There are dense clusters where stars live only a light year apart. In certain regions of the Milky Way, stars form in such high numbers that they end up packed very closely together. In these dense clusters, the distance between neighboring stars can be as small as 1 light year, far closer than the distance between the Sun and its nearest companion. The intense gravitational pull within these clusters influences the motion of each star. Their combined light creates brilliant scenes that would fill the sky for any planet orbiting within such a cluster. Over time, these groups gradually lose stars as gravitational interactions push some outward. However, the densest clusters remain tightly bound for long periods. Studying them provides insight into the earliest stages of stellar evolution and the environments in which many stars are born. These compact clusters show that the Milky Way contains regions of both solitude and incredible crowding. They offer a glimpse into the vibrant communities where stars begin their lives. The galactic center contains arcs of energized gas that twist like ribbons near the heart of the Milky Way. Clouds of gas become energized by the intense radiation and magnetic fields surrounding the central black hole. These forces shape the gas into long, graceful arcs that twist and curve like ribbons in the dark. The structures glow in radio and infrared wavelengths, revealing their delicate outlines. Many of these arcs trace the paths of magnetic fields that thread through the region. Others form where energetic particles collide with gas, creating bright filaments. Observing these ribbon-like shapes helps astronomers map the complex interactions at the galaxy's center. They show how gas flows, how magnetic energy is distributed, and how past events have influenced the environment. Although these arcs may appear serene, they are shaped by powerful and dynamic forces. Their graceful forms add an unexpected beauty to one of the most extreme places in the Milky Way, where energy and gravity continually sculpt the surrounding space. Some worlds orbit stars that flare with intense radiation throughout the Milky Way. Certain stars pulse with sudden bursts of radiation that surge outward like brief shocks of energy. These flares are caused by rapid changes in the star's magnetic field releasing heat and light far stronger than the star's usual glow. When a planet orbits close to such a star, it experiences sharp waves of radiation that can heat its atmosphere, disrupt its chemistry, or gradually strip away its upper layers, yet some planets endure these harsh conditions, developing atmospheres that adapt over time. Observing these systems helps astronomers understand how flares shape planetary environments and influence the potential for habitability. The intensity of the flares varies, with some stars erupting only occasionally while others release bursts on a frequent schedule. These planets experience skies that can brighten, suddenly transforming their atmospheres with each flare. The idea that entire worlds orbit such volatile suns adds a dramatic sense of diversity to the galaxy. It shows that life and stability are shaped by forces far beyond simple sunlight, and that stars themselves can be restless, changing the conditions of any world that circles them. The Milky Way holds enigmatic gamma burst sources hidden throughout the galaxy, are rare objects capable of releasing brief flashes of gamma radiation, the most energetic form of light. These bursts are sudden, short-lived, and incredibly powerful. Some occur when dense stellar remnants collide, while others may form through magnetically driven events in compact stars. Because gamma bursts happen quickly and fade rapidly, they are difficult to observe. Instruments must be watching at exactly the right moment to detect them. When these bursts are captured, they provide valuable insight into extreme physics. The energy released in a single burst can exceed the total output of many stars combined, yet the event may last only seconds. These powerful flashes illuminate the environments around their sources, revealing conditions that cannot be reproduced anywhere else. Studying them helps astronomers probe the nature of magnetic fields, gravity, and dense matter. Even though these bursts are rare, their presence shows that the Milky Way hosts events of astonishing intensity. They offer glimpses into the most powerful processes shaping the lives of compact stars. There are regions where stars form in chains, like beads. In some areas of the Milky Way, stars do not form in clusters or scattered groups, but instead appear in long, narrow chains. These bead-like formations arise when gas in a molecular cloud becomes compressed along a single filament. As the filament contracts, it breaks into regularly spaced pockets that collapse into stars. The result is a line of newborn stars following the shape of the original gas structure. Observing these chains reveals how gravity, turbulence, and magnetic fields work together during star formation. The evenly spaced stars provide clues about the conditions inside the filament before it broke apart. These formations change over time as the young stars ignite and their radiation shapes the surrounding gas chains of newborn stars. Help astronomers understand how large-scale structures within the galaxy influence small-scale events. They show that even simple lines of gas can give rise to elegant and orderly patterns of starlight. These beaded stellar regions add a delicate beauty to the Milky Way's star-forming areas. The galaxy contains enormous clouds that block entire patches of starlight. The Milky Way holds giant clouds of dust and gas so thick that they obscure all the stars behind them. These dark nebulae appear as empty spaces when viewed from Earth, yet they are full of material. The dust grains inside absorb and scatter visible light, hiding entire regions of the galaxy from sight inside. These clouds' temperatures are extremely low, allowing molecules to form in sheltered environments. Over time, gravity can cause parts of the cloud to collapse and create new stars. Although these regions look empty, they are among the most active and important parts of the galaxy. Infrared and radio observations reveal the hidden structures inside them, showing dense knots of gas where future stars will ignite. These massive clouds shape the appearance of the Milky Way, carving dark lanes through the bright band of starlight. Their quiet presence reminds us that what looks like darkness can often hold the beginnings of creation. Some red dwarfs burn so slowly they could outlive the universe. We know red dwarfs are the smallest and coolest stars capable of sustaining nuclear fusion. Their low mass makes them incredibly efficient at using their hydrogen fuel. As a result, they burn at a slow, steady pace and can live for trillions of years. This lifespan far exceeds the current age of the universe. Many red dwarfs that form today will still shine long after more massive stars have faded into remnants. Their gentle glow and stable radiation make them common hosts for planets. Because they live so long, any worlds orbiting them have enormous spans of time to evolve studying red dwarfs helps astronomers understand stellar lifetimes and the future of the galaxy. These stars are quiet, persistent sources of light that dominate the Milky Way's population. Their endurance provides a sense of cosmic continuity and hints at how the galaxy might look in distant epochs. When only long-lived stars remain, the Milky Way holds hidden star factories buried in dark dust. Deep within the densest clouds of dust, the galaxy hides star-forming regions invisible to ordinary telescopes. These hidden star factories are so well shrouded that even starlight from newborn suns cannot escape invisible wavelengths. Infrared observations reveal their presence, uncovering clusters of young stars still in the early phases of formation inside these dark regions. Gas collapses under gravity, assembling new stars from cold material. The surrounding dust plays an important role by shielding the forming stars from harsh radiation. As the stars grow, their winds gradually carve openings through the dust, allowing their light to emerge. These concealed nurseries are among the most active areas in the galaxy, producing new generations of stars that will eventually populate the spiral arms. They remind us that much of the Milky Way's activity occurs behind thick veils of dust, far from direct view. Some stars are kicked to extreme speeds when their companions explode. When a star in a binary system explodes as a supernova, the sudden release of energy can disrupt the delicate balance that holds the pair together. If the surviving star is flung outward at the right moment, it can be propelled to extraordinary speeds. These runaway stars move far faster than typical stars in the Milky Way. Their high velocities reveal the violent events that set them in motion. As they travel, they carry with them the chemical signatures of their original environments. Studying these stars helps astronomers understand the outcomes of stellar explosions and the dynamics of binary systems. Their rapid motion also provides clues about the gravitational landscape of the galaxy. These swift stars remind us that even the seemingly peaceful sky holds records of dramatic and energetic processes. The galaxy contains solar systems with planets that circle in wildly tilted orbits. Not all planetary orbits align with the equators of their stars. Some planets move on steeply tilted paths, circling their stars at sharp angles that differ greatly from the orbits of their siblings. These tilted orbits can arise from past interactions with other planets, passing stars, or the gravitational pull of a distant companion. The unusual angles affect the climate and long-term stability of the planet's seasons can become extreme, and the length of daylight can vary dramatically. Observing these systems helps astronomers understand the chaotic processes that shape planetary architecture. The presence of tilted orbits shows that solar systems can evolve in surprising ways, creating arrangements far different from the orderly pattern seen in our own system. These worlds highlight the diversity of planetary motion in the Milky Way. Some worlds are covered in ice that never melts in the far reaches of the galaxy, or in systems where stars emit only faint heat. Some planets remain frozen from surface to core. Their icy crusts can extend for kilometers, sealing away oceans or rocky interiors beneath solid layers. These worlds may have atmospheres too thin to trap warmth, or may orbit stars so cool that temperatures never rise above freezing. Some exist as rogue planets drifting in total darkness, where internal heat gradually fades until the surface becomes completely frozen. Although these planets seem quiet, their interiors may still harbor activity if enough heat remains from their formation. Studying frozen worlds helps astronomers understand how planets lose heat and how different environments evolve their silent, unchanging surfaces. Contrast sharply with the dynamic weather and geology seen on warmer planets. These icy worlds show that the Milky Way contains environments where cold dominates completely. The Milky Way holds electric charged nebula that glow with ghostly light. Certain nebula in the galaxy emit a faint, eerie glow created by charged particles moving through magnetic fields. These electric charged regions occur when energetic radiation strips electrons from atoms, creating ionized gas. As electrons recombine with ions or move through magnetic structures, they emit soft, ghost-like light detectable in various wavelengths. These nebula often form near hot stars or in regions shaped by past explosions. Their appearance reveals the presence of powerful forces acting on the gas. Observing them allows astronomers to trace magnetic fields that are otherwise invisible. The glow carries information about temperature, density, and the processes that energize the gas, these nebula add a subtle, ethereal beauty to the Milky Way, showing that even faint light can tell rich stories about the energy flowing through space. There are stars here that form in triple systems in some regions of the Milky Way. Stars do not form in pairs or alone, but in groups of three, bound together by gravity. These triple systems begin inside dense clouds where several fragments collapse at nearly the same time depending on their masses and distances. The three stars can arrange themselves in stable patterns. Often two stars orbit closely while the third travels farther out. In other cases, all three follow elongated paths that weave around their shared center of gravity. These intricate motions can remain stable for millions or even billions of years. Studying triple systems helps astronomers understand how stars influence one another from their earliest stages. Their interactions can affect the formation of planets, shaping their orbits or preventing them from forming entirely. Some triple systems become unstable as the stars evolve, eventually breaking apart and sending one member drifting into the galaxy. Others remain connected for their entire lifetimes. These groups reveal the complex and varied environments in which stars are born. They show that gravity often creates arrangements far more intricate than simple solitary stars. Some worlds orbit their stars on paths so eccentric they freeze and boil in 1 year. There are planets in the Milky Way that follow extremely stretched orbits. Instead of circling their stars in nearly circular paths, they move along ellipses that carry them from distant cold regions to scorching close approaches during each orbit. When these planets travel far from their stars, their atmospheres can freeze, forming layers of frost or thick clouds of ice crystals. As they swing inward again, temperatures rise rapidly, ice melts, gases expand, and entire atmospheres can shift in a matter of weeks. These dramatic fluctuations create environments unlike anything on Earth. The surfaces or skies of such worlds constantly transform, shaped by cycles of boiling heat and freezing cold. Eccentric orbits often form through close encounters with other planets or the gravitational pull of distant companions. Studying these wild paths helps astronomers understand how planetary systems evolve after chaotic interactions. These extreme worlds reveal how profoundly orbital shape can influence climate and habitability. The galaxy contains clouds heated by invisible radiation from distant events across the Milky Way. There are clouds of gas warmed by radiation from sources so far away that the heating effect seems almost mysterious. These clouds do not always lie near young stars or supernovas yet. They glow with temperatures higher than expected. Their warmth comes from high-energy photons traveling long distances through space. These photons can originate from ancient explosions, active regions near the galactic center, or compact objects that emit powerful radiation. When the photons encounter gas, they transfer energy and cause the cloud to heat. Observing these warmed regions helps astronomers map the flow of radiation across the galaxy. It reveals how past events continue to influence areas far removed from their sources. These heated clouds act as delicate traces of energy that move silently through space. They show that the Milky Way is filled with subtle interactions between light and matter, even in regions that appear quiet and dark. Some planets are sculpted by tidal forces into distorted shapes. When a planet orbits very close to its star or shares its system with a massive companion, tidal forces can stretch it out of a perfect sphere. These forces arise from the uneven pull of gravity across the planet's surface. The side facing the star feels a stronger tug, while the far side feels less. Over time, the planet can become elongated, taking on a shape slightly like an egg or tear. This distortion affects the planet's interior, generating heat through friction. The extra warmth can drive volcanic activity or alter atmospheric circulation. Some distorted planets orbit so close to their stars that one side remains permanently heated while the stretched shape enhances the temperature difference. Observing these worlds helps astronomers understand how gravity shapes planetary bodies. They show that planets are not always round and that intense gravitational interactions can sculpt entire worlds into unusual forms. The Milky Way holds regions filled with primordial hydrogen scattered throughout the galaxy. Are pockets of hydrogen that have remained largely unchanged since the earliest eras of the universe. These regions contain gas that existed before many generations of stars were born, while much of the hydrogen in the Milky Way has been processed through stars and enriched with heavier elements. These primordial areas preserve a simpler chemistry. Their presence helps astronomers trace the early history of the galaxy and understand how it grew from smaller structures. These clouds are cold, faint, and difficult to detect, yet they play a vital role by feeding material into star-forming regions. They also allow scientists to compare modern galactic environments with ancient ones. Primordial hydrogen stands as a quiet reminder of the universe's beginnings, still drifting through the arms and halo of the Milky Way. There are stars that collapse into dense remnants without exploding. Not every massive star ends its life in a bright supernova. Some collapse directly into dense remnants without producing an outward explosion. This quiet collapse occurs when the internal structure of the star fails, rapidly causing its core to form a black hole or neutron star with little visible disturbance. The outer layers may fall inward instead of being blasted into space. These silent endings are difficult to observe because they produce few obvious signals. Astronomers search for missing stars that fade without explanation or look for subtle gravitational effects that indicate a compact remnant has formed. These quiet collapses help scientists understand the thresholds that separate explosive endings from silent ones. They reveal a more complex landscape of stellar death, where the final moments of a star's life depend on delicate balances of mass rotation and internal structure. Some worlds are born in chaotic multiple star systems. There are planetary systems in the Milky Way that form within groups of 3 or more stars. These environments are filled with shifting gravitational forces that influence the paths of growing planets. Dust and gas disks twist and wobble, shaping planets that must find stable orbits. Amid competing tugs, some planets end up circling one star in the group. Others find orbits around pairs of stars. In rare cases, planets may orbit all the stars together in wide loops. The chaos of these systems creates a wide range of outcomes. Some planets are ejected and become rogues. Others survive in balanced orbits that remain stable for long periods. Studying these complex systems helps astronomers understand how planets form under extreme conditions. They show that planetary birth can occur even in environments filled with disorder and constant change. The galactic center contains whirling disks of hot dust near the Milky Way's core. Swirling disks of dust encircle the central black hole. These disks glow brightly in infrared light because the dust grains absorb intense radiation and heat. To high temperatures, the material moves in fast spiraling paths shaped by gravity and magnetic fields. As the dust orbits, it interacts with surrounding gas, creating structures that shift over time. Observing these disks helps astronomers understand how material flows toward the black hole and how energy from the core affects the surrounding environment. These glowing spirals reveal the dynamic nature of the galactic center. They show that even dust behaves dramatically when placed in such powerful conditions, forming elegant structures that twist in the deep gravitational well. There are star-forming filaments that stretch like cosmic threads in the Milky Way. Some of the most active star-forming regions take the shape of long, narrow filaments. These structures can stretch for many light-years. Filled with cold gas on the brink of collapse, gravity slowly pulls parts of the filament inward, creating nodes where stars begin to form. The filament itself acts like a spine, feeding material to these growing cores. Observing these cosmic threads helps astronomers understand how large-scale structures and molecular clouds guide the birth of stars. They reveal that star formation is often organized following the flow of gas along elongated pathways. These filaments create a sense of order in the apparent chaos of interstellar clouds, shaping the locations where new generations of stars ignite. Some stars live entire lives in near-perfect isolation, while many stars form in clusters or associations. Some drift so far from other stars that they spend their whole lifetimes almost alone. These isolated stars rarely interact with passing objects. Their environments remain calm, free from nearby radiation or gravitational disturbances. Studying them provides insight into how stars evolve without outside influence. Their planets, if they have any, may experience unusually stable conditions. These quiet stars move slowly through the galaxy, following gentle orbits that keep them far from crowded regions. Their isolation reveals the wide range of environments that exist in the Milky Way. They remind us that not all stars share their space with neighbors. Some shine alone from birth to death, carrying their solitary light across billions of years. The Milky Way holds ancient stellar fossils preserved in their original chemistry. Scattered throughout the Milky Way are stars so old that they preserve the chemical conditions of the early universe. These stellar fossils formed before the galaxy had enriched itself with heavy elements their atmospheres contain. Almost nothing beyond hydrogen and helium, along with traces of a few other elements, created shortly after the universe began, because they have remained unchanged for billions of years. These stars offer a direct window into the past. Their faint light carries information about the primordial environment from which the first stars arose. Many live in the galactic halo where the density of gas and radiation is low enough that they have avoided disturbance. Their stable structures and simple chemistry allow astronomers to measure the earliest patterns of star formation. These ancient stars show how the Milky Way grew from small beginnings into the spiral galaxy we know today. They remind us that even now, ancient relics of cosmic history drift quietly through the galaxy, glowing with the untouched chemistry of the first generations of starlight. Some worlds orbit stars that are barely stable in certain systems within the Milky Way. Planets revolve around stars that live on the edge of instability. These stars may be rapidly burning through their fuel, expanding into early giant phases, or oscillating between different states of brightness. Their internal layers shift and pulse, creating turbulent conditions that can influence orbiting planets. Some of these stars release sudden bursts of energy that alter the temperature and chemistry of the surrounding space. Others experience gradual swelling or contraction that changes their luminosity over long periods. Planets orbiting such stars face environments far more variable than way. Their climates may shift dramatically as the star's output changes. Studying these systems helps astronomers understand how planets adapt to unpredictable sources of radiation. It also reveals the delicate balance required for a star to remain stable. These barely steady suns add complexity to the Milky Way's population, showing that not all stars offer quiet and predictable light. Some shine with restless energy that shapes the worlds around them in surprising ways. There are regions where gravity shapes clouds into sculpted pillars. In many star-forming regions of the Milky Way, vast clouds of gas and dust take on towering sculpted shapes. These pillars form when intense radiation and winds from nearby massive stars carve away the surrounding material. The denser parts of the cloud resist erosion and remain standing as elongated columns. Gravity within these pillars pulls material inward, causing new stars to form at their tips or deep inside their sheltered cores. Over time, the pillars may stretch, twist, or fragment as radiation continues to shape them. Observing these structures helps astronomers understand how powerful forces guide star formation there. Dramatic shapes reveal where young stars are influencing their environment and where new generations are about to emerge. These sculpted forms highlight the delicate balance between creation and erosion in the galaxy. They stand as intricate carvings of gas and dust, shaped by light, gravity, and the turbulent flow of stellar energy. The galaxy contains stars with exotic element atmospheres. Certain stars in the Milky Way display chemical compositions, like those seen in typical stellar atmospheres. Instead of the usual mix dominated by hydrogen and helium, these stars can show strong signatures of rare elements, such as carbon, zirconium, strontium, or even heavier atoms forged in unusual nuclear processes. Some of these exotic stars formed from material enriched by ancient collisions of compact objects. Others developed unusual atmospheres through internal mixing or mass transfer from a companion. Their unusual spectra reveal details. It's about the extremes of stellar evolution and the rare conditions that create such elements. Studying these stars helps astronomers trace the pathways through which heavy elements spread across the galaxy. Their distinctive chemical fingerprints act as clues to events that occurred long before the sun existed. These stars demonstrate the incredible diversity of stellar compositions found in the Milky Way. Their exotic atmospheres glow with the products of rare cosmic processes, offering a glimpse into the most unusual forms of starlight. Some planetary Rings stretch wider than Earth's orbit in the Milky Way. There are worlds whose ring systems dwarf anything seen in our solar system. These rings can extend distances larger than the orbit of Earth around the Sun. They consist of dust, ice, and rocky fragments spread across vast regions of space. Such massive rings commonly form around young planets still gathering material, or around worlds that have captured debris from nearby objects. Their structure is shaped by the planet's gravity, the motion of small moons, and the influence of stellar radiation. Observing these rings reveals the processes that sculpt planetary systems during their early stages. The size of the rings suggests that many worlds undergo dramatic periods of collision and fragmentation.
Oh.
These enormous structures shimmer faintly in starlight, forming broad, delicate halos that sweep across their host planets. They demonstrate the incredible range of scale that exists among planetary systems, far surpassing the familiar rings of Saturn. The Milky Way holds stellar remnants that drift slowly through the dark after stars exhaust their fuel. Some collapse into compact remnants that emit only faint light. These stellar remains include white dwarfs, neutron stars, and black holes that move quietly through the galaxy. Many drift alone, far from where they were born.
Their slow journeys carry them through regions of different density and temperature. Some pass through clouds of gas, gathering thin layers of material that produce soft emissions. Others remain nearly invisible, detectable only through gravitational effects on nearby objects. Studying these remnants reveals the long-term evolution of stars and the fate of stellar material. Their presence reminds us that the galaxy contains not only bright and youthful stars, but also ancient survivors of past stellar generations. These drifting remnants embody the final stages of stellar life, moving gently through the darkness long after their parent stars have faded. Some solar systems form with multiple giant planets crowded together. In certain areas of the Milky Way, young stars give rise to systems filled with several giant planets packed into tight orbits. These worlds may begin as large clumps of gas and dust scattered across a disk, growing rapidly as they gather material. When many giants form at once, their gravitational interactions create a dynamic environment. They can push each other into new orbits, swap positions, or even eject one another into deep space. Some systems eventually settle into stable configurations. Others remain chaotic for millions of years. Studying these closely packed systems helps astronomers understand how planetary architectures emerge from complex beginnings. The presence of multiple giants in tight arrangements reveals how flexible and varied planetary formation can be. These crowded systems show that not all solar systems grow with orderly spacing. Some begin as bustling neighborhoods shaped by constant motion and gravitational negotiation. The galaxy contains high-energy arcs formed by magnetic whiplash. In some regions of the Milky Way, magnetic fields twist and snap under intense pressure. When this happens, the sudden release of energy creates arcs of glowing gas that sweep across space. These arcs form when magnetic lines become tangled and then rapidly realign. The process accelerates charged particles, causing them to emit light in radio or X-ray wavelengths. These high-energy arcs may appear near young stars, supernova remnants, or dense regions where magnetic fields are especially strong. Observing them helps astronomers understand how magnetic energy shapes the interstellar medium. The arcs reveal the hidden forces that influence gas clouds, radiation, and cosmic rays. Their appearance adds a sense of dynamism to the Milky Way, showing that even invisible magnetic structures can produce dramatic and beautiful effects. Some stars shed jets that stretch across space for many light years. Certain stars generate narrow jets of material that extend deep into the surrounding space. These jets form when gas spirals onto the star through a rotating disk. Magnetic fields then focus part of the material into thin, fast-moving streams that shoot away at high speeds. In some cases, these jets grow to lengths of many light years, carving tunnels through nearby clouds. The jets can glow brightly where they collide with gas, forming knots and arcs of light. that drift over time. Observing these structures helps astronomers understand how stars grow and how energy moves through star-forming regions. The jets reveal the influence of magnetism and rotation during the early stages of stellar development. Their immense reach demonstrates the power that even young stars can exert on their surroundings. The Milky Way holds worlds that form in darkness far from any starlight. Not all planets form close to bright stars. Some take shape in the outer reaches of young systems, where sunlight is weak or nearly absent. In these distant regions, gas and dust can gather into planets that never receive strong radiation. Their surfaces remain cold, and their atmospheres develop under dim illumination. Some of these worlds may eventually drift inward toward warmer zones, others remain impermanent darkness, orbiting far from any comforting heat. The conditions under which they form differ greatly from the environments near stars. Studying these distant planets helps astronomers understand the full range of planetary birthplaces. These shadowed worlds show that planet formation is not limited to bright and active regions. Even the cold outer edges of disks can create fully formed worlds that move in deep quiet far from the warmth of starlight. Thank you for spending this quiet time beneath the Milky Way tonight. Let the thought of that vast river of starlight linger gently around you, not as something to study or follow, but as a calm presence resting far above the night. The galaxy can stay there in the background, now silent and steady like a soft glow behind closed eyes. If these gentle explorations bring you peace, I invite you to subscribe, or share a thought below. It helps others find their way here. One sleepy soul at a time. As you settle into the quiet, imagine the slow drift of stars far overhead. Imagine the hush between them, the deep stillness that fills the spaces where light takes its time to travel. Let that stillness rise around you. Let it soften your breath and loosen the last tight places in your mind. You do not need to reach for sleep. It will come as naturally as darkness gathering across the sky. If you happen to still be awake, another sleepy video will be waiting whenever you feel ready. And if your eyes are growing heavy, you can let them close and drift gently into rest. Good night.